In this module, we will talk about something which is very interesting, and that is what are ortho-para-hydrogen. In order to understand this, we will be needing the knowledge of statistical thermodynamics, which we have already learned to a great extent, and also some of the concepts of quantum mechanics. First of all, as you know, we have seen in statistical thermodynamics that partition function is the most important quantity in statistical thermodynamics. We call it a storehouse of information. And if we take any diatomic molecule, because we have been mainly focusing on diatomic molecules, for partition function the contribution comes mainly from translational, rotational and vibrational motions. Besides this, in the last module, we also looked into the internal structure of molecules or atoms and noted that electronic and nuclear contributions can also make a significant contribution to the partition function. And therefore, if we have a diatomic molecule, the partition function of a diatomic molecule is the product of translational, rotational, vibrational, electronic and nuclear. In the context of ortho-para-hydrogen, as we will see, nuclear partition function will play a very important role, and we will also introduce the concept of nuclear statistics. If you recall, we showed in the previous module that the nuclear partition function is given by a general relation as shown here, Qn is equal to Gn0 multiplied by e to the power minus epsilon 0 by kBt. And this expression we got because we know that nuclear energy levels are widely spaced apart, and therefore, the contributions of higher nuclear energy levels can be neglected. And if we bring all these energy levels to the 0 of the energy scale, then we noted that the nuclear partition function becomes equal to Gn0, as you can see here. Now, this Gn0 is the degeneracy of the ground nuclear state, and that is what will be equal to the nuclear partition function. All this we have learnt in the earlier module. Now, for a diatomic molecule, it is important to note that the degeneracy of the ground state for determining the nuclear partition function will ultimately depend upon the nature of the atom constituting the diatomic molecule. And we already know, as you can see in this table, that if the nucleus contains even number of neutrons and even number of protons, then its nuclear spin quantum number I is 0. Examples are carbon 12 or oxygen 16. If both number of neutrons and number of protons are odd, so that n plus p is even, as is the case with deuterium and nitrogen 14, then in that case the nuclear quantum number would be integer. And if n plus p is odd, then it will be half integer, as is the case in hydrogen atom H1 or in Cl35. So, if I is the nuclear quantum number of a diatomic molecule, that means of an individual atom constituting the diatomic molecule, then the total number of nuclear states which will be possible for a diatomic molecule will be 2I plus 1 square. This we have already learnt. If we deal with the hydrogen molecule H2, then in this case I will be equal to half. and for this diatomic molecule there will be out of total spin states which will be 2I plus 1 whole square, there will be symmetric spin states that will be equal to 2I plus 1 into I plus 1. These will be even states, we will call them ortho state, and number of antisymmetric spin states would be 2I plus 1 into I. These will be odd states or we will call them para states. So, what I mean to say is that please remember that for any diatomic molecule, once we know the degeneracy of the ground nuclear state, which is, as you know, we have already done for a diatomic molecule, total degeneracy will be 2I plus 1 whole square. Then out of this there will be symmetric spin states, its number will be 2I plus 1 into I plus 1, and there will be antisymmetric spin states and their number will be 2I plus 1 into I. Now, using this concept of symmetric and antisymmetric spin states, we will try to explain the concept of ortho and para hydrogen. Hydrogen molecule, as you know, is a diatomic molecule in which the nuclei of the two atoms are spinning. Depending upon the direction of the spin of the nuclei, the hydrogen molecule can be categorized as ortho or para hydrogen molecules. Hydrogen atom, as you know, has a spin quantum number I equal to half. Now, this can be, as you know, upward or downward as it is shown here. If it is upward, we call it alpha and that is plus half, and if it is downward, we call it beta and this is minus half. Now, what are hydrogen ortho molecules and what are the hydrogen molecules in para state? Ortho hydrogen molecule will be that molecule in which the spins of both the nuclei are in the same direction. That means I total will be half plus half equals 1. And para will be those hydrogen molecules in which the spins of both the nuclei are in the opposite directions. That means I total will be, one is positive, one is negative, half minus half, that makes it 0. But if you calculate the number of symmetric spin states according to the formula which we have already discussed, the number of symmetric spin states will come out to be 3, because that is equal to 2I plus 1 into I plus 1 and I is half. And if you calculate the number of antisymmetric spin states in this case, they will come out to be 1, 2I plus 1 into I, that is 1, and this is corresponding to the para state. The total number of states, as we know, for hydrogen molecule will always be 4, 2I plus 1 whole square. Now, please remember that hydrogen atoms are fermions and they have half integral spin. Therefore, according to Fermi-Dirac statistics, the wave function psi total, now we are using the concepts of quantum mechanics, the total wave function must be antisymmetric. That means odd with respect to interchange of nuclei. Now, let us see what is the consequence of this nuclear spin symmetry. Since H2 molecule has to have the total wave function to be antisymmetric, that means psi total 1 2 should be equal to minus psi total 2 1 antisymmetric. That means, if you interchange the nuclei 1 and 2, it should change sign. Had it not been antisymmetric, had it been symmetric, then the sign would not have changed. Psi total 1 2 would have remained psi total 2 1. As I mentioned it earlier, the total wave function for a molecule is always expressed as psi translational, psi rotational, psi electronic and psi nuclear. It is the product of all these. Psi translational, psi vibrational and psi electronic are even functions for H2 case. That means they are not going to change sign as a consequence of interchange of the nuclei. However, rotational wave function is influenced by nuclear spin symmetries. Psi rotational in the rigid rotator rotational wave function, which can be symmetric or antisymmetric. If you recall the wave function for a diatomic molecule, assuming it to be a rigid rotator, then we have the wave function which is spherical harmonics, and this psi j, that is the rotational partition function, it is symmetric for j is equal to even values, because j is the rotational quantum number, and it is symmetric means it is symmetric with respect to exchange of nuclei, and for odd values of j, psi j, it is antisymmetric with respect to exchange. If we try to express in terms of nuclear spin symmetries, the symmetric and antisymmetric states, they will be, as you can see here, symmetric states would be alpha 1, alpha 2. Second possibility is beta 1, beta 2. Here 1 and 2 refer to the nuclei, and alpha are spin upwards and beta are the spin downwards. And the third possibility is alpha 1, beta 2 plus alpha 2, beta 1. In all of them, why we call them symmetric spin states? Because if you interchange 1 and 2, ultimately the wave function remains unchanged, and there will be a corresponding another antisymmetric spin state which will be expressed as alpha 1 beta 2 minus alpha 2 beta 1. Here if you interchange the nuclei 1 and 2, as you can see here, it will change sign, it will become negative of its original value. Now, for hydrogen molecule, since hydrogen atoms are fermions, therefore psi total has to be odd. So, how is it possible? This is possible only if psi rotational with j even is paired with odd psi nucleus, because we want psi total to be odd. Therefore, psi rotational with j even has to be paired with odd psi nucleus, only then it will become odd. And secondly, psi rotational with j odd has to be paired with even psi nuclear, only then it will become odd. So, now we also know that there are 3 times more even nuclear spin states. If you remember, there were symmetric spin states 3 in comparison to the antisymmetric state 1. Therefore, one can say there are 3 times more odd rotational states which are available, because each odd rotational state can have 3 possible nuclear spin functions. In other words, the degeneracy of the odd rotational levels is effectively 3 times that of the even levels. This is very, very important. Therefore, this leads to a probability distribution which is a function of j, and that will now look like this. This is the probability distribution. For you can see here that for odd states, it is 3 times more than the corresponding even states. This is a very, very important thing. You must have read it in your spectroscopy courses on rotational spectra. So, now what do we say conclude from here? The conclusion is that ortho hydrogen molecules will be those with odd j values, while para hydrogen molecules will be those with even j values, because ultimately the total wave function has to be odd, and that is possible only in this way. So, now the question comes, if that is the case, then what does hydrogen molecule actually constitutes? What is the composition of the hydrogen molecule? That is basically the next question which we will try to answer now. This answer is provided by statistical thermodynamics. If one determines the standard entropy for hydrogen molecule experimentally, it comes to be 124.0 joules per K per mole. That is the experimental standard entropy for hydrogen molecule. On the other hand, if you calculate this using statistical mechanics, then its value comes out to be 130.6 joules per K per mole. So, there is a difference between statistical calculation result and the experimental value of entropy of hydrogen molecules. So, the question is, how do we account for that? Here the concept of ortho and para hydrogen, which we discussed earlier, that will be able to account for this discrepancy which we are observing. We know that hydrogen molecule consists of two types of molecules. One is those that where we have the molecules with rotational quantum numbers are odd, and these molecules have 3 nuclear spin states. This can be explained on the basis of the fact that when the rotational quantum numbers are odd, we saw J is equal to 1, 3, etc., then there are 3 nuclear spin states which are available. And when the rotational quantum numbers are even, there is only one nuclear state which is available. So that we can now say that both the kinds of hydrogen, both ortho and para isomers of hydrogen are present in the ordinary gas. That means it is not only one type, it is containing a mixture of ortho and para hydrogen. If you look at the partition function of the hydrogen molecule, especially the rotational partition function, the general expression is as it is shown here, QR is equal to summation I g g j e to the power minus epsilon j upon k b t upon I. That means it is over all rotational states. The equation can be written as QR is equal to 3 times summation j odd, this summation is over odd values, plus 1 times, these 3 and 1 come because of that nuclear spin states. And for odd there are 3 states available as we mentioned, and for even 1 state is available. So, this Gj is the corresponding degeneracy of the rotational energy level, and epsilon j refers to the rotational energy. This degeneracy Gj we have already discussed, and it is 2j plus 1, and the corresponding rotational energy levels are given by j into j plus 1 h square upon 8 pi square I. Therefore, you can see here, if we expand them further, we notice here that the rotational partition function for hydrogen molecule will be a mixture of these two, 3 times j odd 2j plus 1 e to the power minus j into j plus 1 theta r upon t. Here theta r is the rotational temperature which we have already discussed in the context of rotational partition function in our earlier modules, plus 1 into summation j even into 2j plus 1 e to the power minus j into j plus 1 theta r upon t. Theta r is the rotational temperature and it is given by sigma h square upon 8 pi square I k p. So, what we really need to emphasize is that ordinarily hydrogen is a mixture of ortho and para hydrogens. And as you can see from this graph, what will be the percentage of ortho and what will be the percentage of para, this depends upon temperature, as you can see here. At very low temperature, if we go to the extreme left, it is 100% para. That means it is possible to get hydrogen in pure para form at very low temperatures. But if you go to higher temperature, maybe at room temperature, the maximum composition which one can get of ortho, as you can see here, is 75%. Para will be 25 and ortho will be 75%. So, you can never get hydrogen as a mixture of 100% ortho, that is not possible, and the maximum which you can get is in the ratio of 3:1. So, this is a very important point, and if this is taken into calculations, then one notices, as you can see here, because of the mole fraction becoming 0.75, as you can see here, there is a additional contribution which is coming to the rotational entropy, and that is basically because of nuclear isomerism and nuclear degeneracy. This is a sum total of this, and this contribution is equal to delta S rotational, which is 0.75 R. This 0.75 is coming from 3/4, because in a mixture maximum you can have is 7.775% into R into ln 3, and that gives you a contribution equal to 6.851 joules per K per mole. So, if this is the additional value which we have been considering, therefore, if this value delta S rotational is subtracted from the statistical calculation of entropy, statistical calculation of entropy had given a values of 130.6. Now, if we subtract 6.851, we get 124.0, which is the same as the experimentally determined entropy value. So, you can see that nuclear statistics really explains the concept of ortho and para hydrogens. Ortho and para hydrogens basically arise because of the degeneracy of the nuclear state. There are symmetric states, there are antisymmetric states, then symmetric states need to be combined with odd rotational levels, and antisymmetric need to be combined with even rotational levels, and that gives rise to hydrogen as a mixture of ortho and para. So, this is a very important concept, and that shows a very good applications of statistical mechanics. To summarize what we have learnt in this module, we have seen that the nuclear contribution ultimately to the partition function is equal to the degeneracy of the nuclear state, and this is equal to, for a diatomic molecule, 2I plus 1 whole square. The value of I, the nuclear quantum number, ultimately will depend upon the number of neutrons and protons present in the nucleus. In the case of hydrogen molecule, I is equal to half, and therefore, there will be 4 the value of degeneracy. Out of this, 3 will be symmetric states and 1 will be antisymmetric states. In general, the formula is 2I plus 1 into I plus 1, that is the symmetric or even states, we call them ortho, and then the number of antisymmetric states will be 2I plus 1 into I, we call it odd states or para. Then we also discussed in this module that for hydrogen molecule, which is a diatomic molecule, ortho molecules will be those in which the spins of both the nuclei are in the same direction, whereas para hydrogen molecules will be those where the spins are in the opposite directions. We also emphasize that since hydrogen atoms are fermions with half integral spin, therefore, the total wave function of hydrogen molecule must be antisymmetric with respect to the interchange of the nuclei. And lastly, we said that for the case of hydrogen molecule, the standard entropy for hydrogen is 124.0 joules per K per mole, which is found by measuring the heat capacity experimentally. The value obtained using statistical calculation was not in agreement with this, and it was coming out to be 130.6, and this discrepancy, as we showed, is accounted by nuclear and rotational degeneracy, and this contribution comes out to be 6.851. And if we subtract this from 130.6, we get a value which is close to experimental entropy.